Hello, hello. Can you hear me? Hello. You are on mute. You have to unmute yourself.
Hello?
Yeah. Can you hear me?
Yes.
Okay. So today we'll start off with some new topics in number theory. The first thing is basically the division theorem. So you have already seen this before in lower classes, but it has not been stated like this, and we need to understand how to formally state it and how we will be using it in problems. So we need to understand that. So it goes like this. For all integers a and b with b greater than 0, there is a unique pair of integers q and r such that a is equal to b times q plus r, where 0 is less than equal to r and r is less than b. Here what we are doing is we are dividing a by b. Dividing a by b, and we are getting q as the quotient and r is the remainder. And you can see that the condition says that the r value must be between 0 and b, right? So b
Yes.
is the divisor and a is the dividend. So when we divide a by b, you get q and r, where r is the remainder. The remainder has to be less than the divisor, right?
Yes.
And also, there is always a unique pair of integers q and r. So that means there is only one way to divide a by b. You will not get two integers q and r and some other pair of integers which will also be satisfying this condition, right?
Yeah.
So what that means is, if I say something like this, a is equal to bq1 plus r1, and let's say bq2 plus r2, I'm right now saying that q1 and r1 is one pair and q2 and r2 is another pair. This is not
Yeah.
possible. So we can prove it like this. So we can say that if these two things are, we are trying to prove by contradiction. So if this is actually true, then we will be able to write b times q1 minus q2 is equal to r2 minus r1, right?
Yes.
And since both of them are supposed to be remainders, we know that 0 is less than r1 is less than b, and we also know 0 is less than r2 is less than b, right?
Right.
We can assume without any loss of generality that, let's say, r1 is greater than r2.
Yeah.
It could be either way, doesn't matter. We can assume r1 is greater than r2, and since q1 is not equal to q2, therefore we can say that mod of q1 minus q2 is greater than equal to 1. They will be different by at least one integer, right?
Yeah.
Since we are saying that they are different, Q1 and Q2 are not same, so at least this much is true. So then we can say that B is greater than R1 from here, and we have assumed R1 is greater than R2. So it is also greater than equal to R1 minus R2.
Yes.
This statement is true, right?
Mm-hmm.
Basically, R1 is greater than R1 minus R2.
Right.
And that this part, R1 minus R2 is equal to, we can say is equal to mod of R2 minus R1. And the mod of R2 minus R1 can be written as this, right? Mod of this.
Yeah.
Mod of B, mod of Q1 minus Q2, right? And
Right.
we can say that this thing is greater than equal to mod of B into 1 from here.
Right. Yes.
So what we are getting now is B is greater than this. This is a strict inequality. And afterwards we have got inequalities here and this is greater than this. This is
Yes.
impossible, right?
Right. Yeah.
We had a strict inequality at this end, and now after some inequalities, we got that that is greater than equal to this, which is not possible, right?
Right.
So, which means that there cannot be two pairs of integers like this.
Right. Yes.
So, it is a unique pair that we get when we divide two numbers. And basically, you should also understand that when I'm saying A is equal to BQ plus R, here the Q value is the greatest integer less than equal to A by B. Here, this symbol stands for GIF or greatest integer less than equal to N. Greatest integer less than or equal to. If I put N here, it is less than or equal to N. You have seen this before? Have you seen this
Yeah, yeah,
GIF
yeah. I've
function?
seen this. I've seen this. A floor function.
Yeah. So the floor function, or basically it means if you do 5 by 2, GIF will be 2. But if you do 4 by 2, if it is an integer, it is also it's the same thing as whatever the integer is, right? So
Yeah.
GIF of 1.3, GIF of 1.3 is equal to 1. GIF of minus 2.1 will be what?
Uh, -2.
No,
Oh, greater integer, yeah, -3.
no, it has to be less than or equal to n, right?
Yeah.
You cannot put negative 2. Negative 2 is greater than this.
Right. Yeah.
It's always the integer lower than the number or equal to it. If it was -3, GIF is -3. Whenever you
Yes.
put input as an integer, the GIF will be the same integer. But if it is not an integer, it will be some integer less than it. The largest integer less than that one.
Right.
So here, the quotient is actually the GIF of A by B, right? So we
Yes.
can write the remainder as A minus B times GIF of A by B.
Right.
So this thing you should know that what is actually the remainder and the quotient. Then let's talk about one important thing that comes out of this definition, and that is the idea of residue classes. So this is a very important idea which we will come back to many times in the future. But for now, let's try to define it. So let n greater than equal to 1 be an integer, be an integer. Now, according to the remainder, according to the remainder given by an integer x, given by an integer x upon division by n, upon division by n, x can be in one and only one of the sets of integers. Sets of integers. What is this set? M R n is equal to nq plus r such that q belongs to integers and r belongs from 0, 1, 2 till n minus 1. So let's try to understand what I have written here. So we are saying that when the integer x is divided by n, right, then x
Yes.
can be in only one of the sets of integers, and these are the different sets. What are the different sets? We can say first set is m1n, which is numbers of the form nq plus 1 when q belongs to z.
Yeah.
So this set is the set of all numbers of the form nq plus 1, where q is an integer. So basically this is always going to leave remainder 1, right?
Yes.
When the number is divided by n. So when x is divided by n, since x is of the form nq plus 1, it will leave remainder 1, right?
Yeah.
Or m2n could be numbers of the form nq plus 2, where q belongs to integer, right?
Yeah.
And so on till n minus 1 n, where it is of the form nq plus n minus 1, where q belongs to integer, right?
Yes.
So we are saying that whenever you divide a number by n, your remainders could be anything from 0, 1, 2 till n minus 1, right?
Right.
So any integer x upon division by n can only be in one of these sets, right?
Yes.
The x integer has to be in one of these sets. It cannot be in two different sets, obviously.
Right.
It will have any one of these forms, right?
Yeah.
So these sets M, R, N, where this bracket here denotes we are dividing by n, and the R here subscript denotes what is the remainder or residue when we divide by n, right?
Yeah.
So it is numbers, it is made up of numbers of the form nq plus r, where r is the remainder and q is obviously an integer, right?
Yeah.
So for example, that means that m0n, what does that mean? It is consists of all integers divisible by n.
Yeah.
All integers divisible by n, because m0 1 will be of the form nq plus 0, where q belongs to z, right?
Yeah.
Okay. Similarly, m01, if you think of when you divide by 1, it will be numbers of the form 1q plus 0, where q belongs to z, right?
Yeah.
And actually, you will realize that whenever you divide by 1, you only get this 0 remainder, right? Always.
Right.
So actually, this set is the set of all integers z. Because notice, when you put it in the normal form of the set, you're getting 1q plus 0, where q belongs to z. Q belongs to
Yeah.
z means it's the whole set of integers,
Right.
right? And if I do m02, for example, right, you will get, when you divide by 2, so 2q plus 0, where q belongs to z, right?
Yeah.
So basically, it is the set of all numbers which are of the form 2q. So these are all even numbers, right?
Right.
Do you understand what I'm saying?
Yes.
So all of these sets M, R, N, there are how many such sets? R goes from 0 to n minus 1. So there
Yeah.
are n sets, right? These are known
Yes.
as, these are given the name residue classes modulo n. So basically the residue means remainder. So it's the different classes of remainders. So there are n residue classes modulo n, right?
Yeah.
And basically it is producing a partition of the set Z of integers, right?
Yes.
MRN, the n residue classes forms a partition of the set of integers. What I mean by that is the integers can all be said to lie in one of these n classes, right?
Yeah.
All integers will lie in one of these sets, and there is no integer that will be outside all of these sets. So basically what I'm saying is set is this is Z, then these are my residue classes, and this might be M1 and M2 and this is my Mn minus 1 n, right?
Yes.
What I can say is like there is no integer here which is not in one of these classes for sure, right?
Right.
And all of these classes are mutually exclusive. They are not, there's no intersection between any classes, right?
Right.
And that is what is a partition. Basically, it divides the set completely, and nothing is left over, right?
Yeah.
So when you are using n is equal to 2, we know that the set of integers has to be divided into two residue classes, even and odd.
Yes.
Either your remainders are 0 or your remainders are 1. These are the two residue classes, M0, 2 or M1, 2, right?
Yes.
So this is a very important idea. We'll use it many times in questions later. So just keep that in mind. Uh, the next thing I want you to try is a couple of problems. Uh, these are important problems because they will show you the power of the division algorithm. So this is first one. Let A is greater than equal to 2. M and N are positive integers. Suppose that M divided by N leaves a remainder R, then show that the remainder of A power M minus 1 when divided by A power N minus 1 is A power R minus 1. That is the first problem. And the second one is, you can write this down as well. Let A is greater than equal to 2 and M is greater than equal to 2 be integers such that A power K minus 1 is divisible by M for some positive integer K, positive integer K, and let N be the smallest positive integer for which m divides a power n minus 1, m divides a power n minus 1, that is n is equal to minimum of k belonging to n positive, where m divides a power k minus 1. We have to prove that for a positive integer k, a power k minus 1 is divisible by m if and only if k is divisible by n. So focus on the first problem first, and then we'll think about the second one. Okay. So these two problems we have to do right now, and then we'll go ahead. Try it out. You have 10 minutes. Think about it calmly and figure it out. Okay.
Yes.
Yeah, I'll be back in 5 minutes. Just try these out. Are you getting something for the first one?
So what I did so far, I said that m is equal to like bn plus r, kind of like the division theorem.
1 second.
Yeah.
We have to, right. So we were saying they had given us that m divided by n leaves remainder r. Leaves remainder r. And we have to find the remainder or prove that when we divide a power m minus 1 divided by a power n minus 1, we will get a power r minus 1 as remainder.
Yeah.
So this statement has been given. So therefore we can write m is equal to, you should write qn plus r. That will be better because b is a, q tells us its quotient.
Okay, yeah.
M is qn plus r, that much we know. Then a power m minus 1, how can we rewrite it? We can write it as a power qn plus r, right? Minus 1.
Yeah.
Okay. So this is the point where you have to think about it. We have to divide it by a power n minus 1, right?
Yeah.
So, and prove that the remainder is a power r minus 1. So one thing we can see here is that this is a power qn times a power r, right?
Yeah.
So what can we do here?
You could.
See, what we can do is we can add and subtract an a power r. I'm saying this, right? That
Yeah.
hasn't changed anything, but that has helped us take a power r common here, right?
Right.
Why is that useful? Because now you can say that if you remember, we had proved that x minus y divides x power n minus y power n.
Yeah.
So we can write the quotient also here. There is that we had discussed previously, right?
Yeah.
So here what do you have? A power qn minus 1, and we have to divide by a power n minus 1, right?
Yeah.
So what? We are raising it to the power q and q, right?
Right. Yeah.
A power n minus 1 will divide this because you can try it out. So we can write it as, keep the a power r untouched. We can write a power n minus 1 and a power, it will be q minus 1 into n plus a power q minus 2 into n plus so on till a power 1 into n plus 1. What am I saying here? Think about it. Uh, x square minus 1 will always divide x power 4 minus 1.
Yeah.
We are using this result.
Right.
You can divide it and see what you will get. A power n minus 1 and a power qn minus 1. We are raising it a power n to the power q minus 1 to the power q, right? Call
Yeah.
this as x and y. You're getting x minus y is dividing x power q minus y power q, right?
Yes.
That's obviously going to work.
Yeah, okay.
So we have been able to write this as a power n minus 1 into this, right?
Yes.
So clearly now if I divide this expression by a power n minus 1, this first term is completely divisible. So remainder will be this only, right?
Yes.
Do you understand what is happening?
Yeah.
So what we have done is written by division algorithm m as this, separated it out like this. The only tricky step is this, because then we get the required remainder, right? And we are also able to take a power r common here.
Right.
And this is a thing that a power n minus 1 will completely divide this, because you can take a power n as x and 1 as y, and you're getting x minus y will divide x power q minus y power q.
Yeah.
So this part is completely divisible by a power n minus 1, and therefore remainder will be this, right?
Yes.
So that is the first problem. Now, the second problem is very important. Let's think about that. In the second problem, he says a is greater than equal to 2, m is greater than equal to 2 are integers such that m divides a power k minus 1
Right.
for some positive integer k. Positive integer k. And we have n is the smallest integer for which m divides a power n minus 1.
Yeah.
Okay. We know that m divides a power k minus 1, and n is the smallest expression of this form where m also divides that, right?
Yes.
Okay. We have to prove that for a positive integer k, m divides a power k minus 1 if and only if n divides k. Okay. So, okay. So let's think about it. So basically what it is saying is, in numbers, if you think about it, it's like saying if the smallest expression of this form, a power n minus 1, m divides that,
Mhm.
then when can you say that it will divide a higher expression, right?
Yeah.
It will divide a higher expression, a power k minus 1 of that same form, only when n, this here power here, divides k, right?
Yes.
So let's think about it. So one side is pretty easy to do. So one side is like saying like if n divides k, right? Then
Yeah.
we know that a power n minus 1 divides a power k minus 1, right?
Yes.
Why? Because if n divides k, then k is equal to some nq, right?
Right.
Do you understand what I'm saying?
Yes.
So this will be a power nq minus 1, and same thing as before, right? A power n to the power q minus 1 power q, right?
Yes.
So obviously a power n minus 1 will divide this thing, correct?
Yes.
So if n divides k, a power n minus 1 will divide a power k minus 1.
Mhm.
So, and if we know that m divides a power k minus 1, No, if we know that, prove that for positive integer m divided by k minus 1. So now we can say from here that if m divides a power n minus 1, then m will divide the higher one, a power k minus 1, right?
Yeah.
Do you understand what I'm saying?
Yes.
N divides k, that implies this is a factor of this. So if I
Yes.
get m is a factor of this, then automatically it will be a factor of this.
Yeah.
So that part of it is pretty easy. So we have proved one side of it. If n divides k, then this, right?
Mm-hmm.
We
Right.
have to prove the other side also, right?
Yeah.
So let's try to do the other side of it. So now we'll assume the opposite, that m divides this, right?
Yeah.
And we'll try to prove that n divides k then, right?
Yes.
Okay. So to prove the other side, we'll assume that m divides a power k minus 1, right?
Yes.
And and let's say k is equal to n q plus r. So when we divide k by n, we get q and r as remainder and quotient, right? So
Yes.
by applying the division theorem, so we can say that definitely r will be less than equal to 0 is less than n, right?
Yes.
Correct, no?
Yeah.
So we can now say that a power r minus 1, uh, one second, we can write this as, we know this fact. This fact is what we need to use. N is the smallest integer for which m divides a power n minus 1. Okay, so a power r minus 1 is equal to a power k minus 1 minus a power nq minus 1 into a power r. See, what have I done here? I have written this as, this is, simplify this out. You will see a power k minus 1 minus a power nq plus r plus a power r, right? And a power
Yeah.
k and this is same, no?
Yes.
So technically this is the same thing, right?
Yeah.
Using division algorithm step, right?
Right.
So now we have this assumption here, m divides this, right?
Yes.
So if m divides this, we also know m divides a power nq minus 1. Why? Because it was given in the problem that m divides this, right?
Yeah.
So this is the same thing as we have been doing before. If m divides a power n minus 1, m will divide a power n q minus 1 per q, right? Because a
Yes.
power n minus 1 will divide this, right?
Yes.
So we know m divides this also, because that is our assumption now, right? And m
Yeah.
divides this also, because that is given in the problem from here.
Yes.
So therefore we know m divides a power r minus 1, right?
Yeah.
Okay. Uh, So a power r minus 1 is divisible by m. So 1 second. What does that mean for us? If m divides a power r minus 1, r is the remainder when we divide n by k, k by n. R is the remainder when we divide k by n. So here, oh wait, now see what is happening. We knew that r was less than n here, right?
Yeah,
Because of this division algorithm that we had written, right?
correct.
Now we are getting m divides this, right? But
Yes.
this is less than a power n minus 1, right?
Right.
Because of obvious stuff, this from here.
Yeah.
But what were we saying? N is the smallest integer for which m divides this, right?
Yes.
But a power r minus 1 is smaller than this, no?
Oh, yeah.
Do you understand what is happening?
Yes.
This is a contradiction, right?
Right.
So this is contradicting the fact that n was the smallest integer such that m divides this, right?
Yes.
So that means uh, r must be 0 then.
Yes.
If it was any other integer, it would give us a smaller integer, right?
Yeah.
Do you understand what I'm saying? If
Yes.
r is bigger than 0, then it will contradict this.
Correct.
So if r is 0 at this step, then we automatically know that n divides k.
Yes.
Like we are saying that if k is divided by n and we get a remainder r, then we have proved that a power r minus 1 is divisible by n.
Yes. Correct.
But a power r minus 1 divisible by m will contradict the fact that n was the smallest integer here.
Right.
So this divisibility must be like complete divisibility. There's no remainder.
Yeah.
Do you understand that we have proved the first side before the direct
Yes.
side?
Yes, I
Now,
understand.
so both sides are done, and like it's not enough to just prove it. You need to like realize in numbers what that means. So think about it like this. For example, if you have 2 power 6 minus 1, which is 63, right?
Yeah.
This is divisible by 9,
Right.
right? If you take any 2 power j minus 1, where j is 1, 2, 3, 4, 5, you will say that none of these are divisible by 9.
Yeah.
You can check it, none of these are divisible by 9, right?
Right.
31, 15, and so on, right?
Yeah.
So what are we getting? This means that 2 power k minus 1. So 6 is the smallest n such that 9 divides 2 power n minus 1, right?
Yeah.
Smallest positive integer for which 9 divides this is 6, right? So if we are checking whether 2 power k minus 1 is divisible by 9, right?
Yeah.
Now we can use the second theorem that it will be divisible by 9 if and only if k is divisible by 6.
Right.
Do you understand what I'm saying right now?
Yes.
The second theorem that we have just now done says that uh, a power k minus 1 is divisible by m if and only if k is divisible by n. K is divisible by n. And what is n? N is the smallest integer. N is the smallest integer where n divides a power n minus 1,
Yeah.
right?
Correct.
So, for example, 6 is the smallest integer for which 9 divides 2 power 6 minus 1, right? So, when we are checking 9, whether it divides 2 power k minus 1 or not, we can just check whether k is divisible by 6 or not.
Yeah. Right.
I hope you are understanding what I'm saying.
Yes, I understand.
Okay, let's do one more problem to reinforce what we have learned so far. So this problem says, is there a power of 2? Is there a power of 2 such that by permuting its digits, permuting its digits, we can obtain a different power of 2. What do I mean by permuting the digits is permuting basically means rearrange.
Yeah.
Rearranging its digits, we can get a different power of 2. So there is some number which is some power of 2. Can we rearrange its digits to get a different power of 2? That is the question.
Mm-hmm.
So here again, we will use what we have learned so far, and this is a nice solution. So I'll just show you. The answer is no, we can't. And the proof is very nice. So let's say x is our number, right?
Yeah.
X is our number and x is some power of 2. Okay. So
Mhm.
if you think of s of x is sum of digits of x. Sum of digits of x, right?
Yeah.
It is very simple to prove that x minus s of x is divisible by 9. We have already done it several times before. If you think of it as a 3-digit number, 100a plus 10b plus c minus
Oh,
a
yeah.
minus b minus c, you will easily get that it is divisible by 9, right?
Yes.
Even if any number of digits you take, always x minus s of x is divisible by 9.
Right.
That's obvious, right?
Yes.
So suppose now that m is greater than n, and by rearranging the digits of 2 power m, we can get 2 power n. That's what we are trying to see whether it is possible or not, right?
Yes.
So obviously, since we have just rearranged the digits, s of 2 power m is same as s of 2 power n, right?
Right.
The digits are the same, we are just rearranging it, right?
Correct.
So now let's think about what we can say about 2 power m and 2 power n. M is bigger than n. So we can say 2 power m can be written as uh, no, we can start with 2 power m minus 2 power n. 2 power m minus 2 power n is equal to 2 power n, and 2 power n common I have taken. So 2 power m minus n minus 1. And here what we will say is we will rewrite this term as 2 power m minus s of 2 power m minus 2 power n minus s of 2 power n. Do you understand what I have done?
Yes.
Now think of this one and this one. There is no difference because s of 2 power m and s of 2 power n are same, right?
Right.
So we can write them like this and like this, right?
Oh, yeah.
Because it's just subtraction and then we have later added it back, right? Nothing has
Yeah.
changed.
Yeah.
But the benefit of writing it like this is that we know that this thing is divisible by n, by 9.
Right.
And this is also divisible by 9, right?
Yes.
So basically, two numbers are divisible by 9. So this is divisible by 9 now. Correct?
Correct.
Do you understand what I'm saying?
Yes.
And 2 power n has no common factor with 9. So that means 9 divides 2 power m minus n minus 1, right?
Yes.
Okay, great. So we have come to this step here. And just now we saw that the smallest number such that 9 divides 2 power n minus 1 is n is equal to 6, right?
Yeah.
And any higher number where 9 divides it in this form must be multiple of 6, right?
Yes.
So first of all, we know m minus n is greater than or equal to 6, right?
Right.
So if it is greater than or equal to 6, that we know, then we can say 2 power m is equal to 2 power m minus n into 2 power n, and that is greater than or equal to 2 power 6 into 2 power n, right?
Yes.
But now notice that 2 power 6 is 64, which is obviously greater than 10 into 2 power n, right?
Yes.
And this automatically means that the number of digits are different now. 2
Correct.
power m is greater than 10 into 2 power n. So this will have one more digit at least, right?
Yeah.
So that means that is not a rearrangement then, right?
Correct.
Basically, we have said that using the conditions of the problem, and using the fact that divisibility by 9 is true for x minus s of x, right?
Yeah.
X minus s of x is divisible by 9, always. We got that 2 power m minus 2 power n is divisible by 9, right?
Right.
Because we assumed that 2 power m and 2 power n can be gotten by rearranging their digits, and therefore we were able to say that this is same as this, right?
Yeah.
And now from here we got that 9 divides this, which means m minus n must be greater than or equal to 6, because 6 was
Right.
the smallest number we have seen, right?
Yeah.
And that automatically contradicts it, because now 2 power m is greater than 2 power 6 into 2 power n. So, which means that it will have more digits than 2 power n.
Right.
Do you understand what I'm saying?
Yes.
So there is no way in which you can rearrange the digits of a power of 2 and end up with another power of 2.
Right.
So keep in mind what we have done so far. The three things, or at least the two things that we proved, are super important. One was the remainder when a power m minus 1 is divided by a power n minus 1, right?
Yes.
The remainder is a power r minus 1, where r is what? R is the remainder when m is divided by n,
Right.
correct?
Yes.
So that result will be very useful in problem solving. The other result that we got was, if you want to see whether some 2 power, for example, if you take a higher example, so if you want to see whether some 2 power 35 minus 1 is divisible by some number.
Yeah.
So let's say 8, right?
Mm-hmm.
Basically, you have to find the smallest number where 2 power n minus 1 is divisible by 8, right?
Yeah.
Find this n, right? Find the
Yes.
smallest number where 8 divides something like this. Then this thing has to be divisible by that smallest number, right?
Right.
For 8 to divide a large number here, do you understand what I'm saying?
Yes.
2 power some big number minus 1 or it's not just restricted to obviously powers of 2, it is valid for any a power something, right?
Yeah.
So anytime you have a divisibility question where a power p minus 1, you have to check whether it is divisible by n or m. Then we can first find the smallest integer such that a power n minus 1 is divisible by m. N is the smallest integer, right?
Yes.
If you find that smallest integer which m divides this, then all we have to check is whether n divides p or not. Do you understand?
Yes.
If n divides p, then m will divide this also.
Right.
Both sides are true and we have done the proof. So make sure that you understand these things. We will be using this in problems later. Okay. So the next class will be doing the AMC problems, but after that we'll continue with number theory here. Okay. Also, next week's class has to be rescheduled. I am not available on Tuesday or Monday night for you. Okay. So I'm out of town. So we can do it either earlier, like we can do the class on, depends on when you are free.
Uh,
So
yeah. I
s-
can't do my Saturday, so I think
Sunday
that's yours.
morning, yeah, that's fine for me.
No, I can't do it because I have a debate tournament.
Your Saturday is not possible.
No, but
Okay.
I can do Sunday, my Sunday, so your Monday.
But Monday morning I'm on a flight, so it's fine.
Oh,
So then we'll do it afterwards.
okay,
So
all right.
So I'm not available from Monday, Tuesday, Wednesday. So Thursday I'll be back, but I don't know whether I'll be back for time for our class. So next
Okay.
week's classes will be a little disrupted. We'll do it whenever we are getting the time. So
Okay. All right.
maybe the next week's class will be your Thursday evening instead. Thursday
Okay.
evening
So you're
and
Friday.
so my Friday and then maybe Saturday evening for you, or Friday evening also is possible. But
Okay, that's fine.
basically we have to shift the classes a little bit for next week. Okay.
Yes.
Okay. That's all for now. We'll continue next class then.
Yep. Thank you.
Bye.